Hello everybody and welcome to this tutorial. In this video I will talk about conjugate heat transfer. So if you see here, I have geometry like heated cylinder inside which is generating heat volumetrically. So the units of heat generation will be watt per meter cube, and we have airflow. So air will flow and take heat away from the inner cylinder, and the other surfaces are like inlet. This is inlet, so air will enter from this side, and this is the exit of air, and the other outer surfaces are considered as the wall boundary condition. So basically this is conjugate heat transfer problem. The heat will be generated inside and it will be carried away via airflow. So before going to this tutorial or solving it, I want to tell you that I have also created a video using design modeler geometry for the same conjugate heat transfer phenomena, and the link is given in description. And if you are more familiar with design modeler, please watch that video. So for this tutorial I will use the SpaceClaim. So first we need to create a circle on this GX plane, and you can give certain dimension, then pull it this surface, and we are going to pull it in both the direction. So just right click, choose this option and pull it in both the directions. So let's give certain dimensions here. I am going to give 30 mm as the dimension, and then we need to create the outer geometry. For that I will select rectangle option, and I will create a new plane that is slightly away from this outer surface to create two separate geometry for conjugate heat transfer. So I will create a rectangle here, and for convenient I will use this option, define rectangle from center. So the reference will be taken from center, and it is going to be symmetric around the center. Now I am going to use this pull option again to create the outer flow geometry, and yeah, I don't need to pull it in both direction, just the bottom direction is going to be enough. So let me do it again. Okay, pull it in bottom direction. So before that maybe you can use this add feature. Give the dimensions of your choice, or you can follow this tutorial dimensions. Now let's look inside the geometry. So for that we use this sectional plane and select a particular plane, and then we can see inside. And now if we zoom it, we can see the multiple diagonal lines, and outer diagonal lines are going inside also. This means we have overlapping geometry. So to sort it out we have to use combine feature, or that is also called the Boolean operation. So for that first we need to select geometries in a specific order. So first I will select the outer geometry, then use this cutter option, and then I will select the inner geometry. So this will create three different parts, and you can see parts separately, like using this multiple diagonal line on cross section. So this means the inner part is created twice, so we need to delete at least once, and then we will have only two parts. One is outer part and one is inner part. So this is the Boolean operation, and this operation is generally used to separate combined geometries or combined solid. Now we can give the name these as solid cylinder or heated cylinder, and we can also give the name in a similar manner for outer part of this geometry or outer flow. So let me give that the name as, since I am going to use airflow for outside, so that is airflow. So you have created this geometry. Now you have to define the boundary. So first create the surface, then go on groups, and then create NS, that is short form for named selection, and then click on that. And now I will give this face as inlet boundary, then there will be outlet. So this surface will be outlet, so you have to follow the same procedure. First click on the surface, go to groups, create NS, and give a particular name. And the other boundaries I am going to choose as the walls, which by default are no slip boundary condition. So let me give the name them as wall. So these four are basically wall, and then we have inlet and outlet. We don't need to worry about the interface conditions, because shared topology in Fluent will take care of that part. So let's go ahead, and so we will start the meshing part now, and we can choose the number of processors. And since we have already created geometry, we just need to import the geometry, since that is available in workbench. So just click on import geometry as a single file, also with the default options. And then it is asking to add local sizing, and for this case we are going to use local sizing near the solid fluid interfaces, and that is very important because of interfacial heat transfer. So here I will use the size control type as the face size, and I will select the heated cylinder as the surface or geometry for creating a local sizing. So let me select the heated cylinder. You can see this is the inner part, and I will also choose the target mesh size, and I will change the default value to the desired value which I actually want, that is 500 micron. And then that's this option, and then I will click on add local sizing. I will show you later how the mesh is generated, and then I will go to generate the surface meshing, and I will define minimum or maximum sizing. You can choose the default value, or you can also change according to your requirement. I will change the minimum sizing, but I will keep the maximum sizing as default value. And you can also change the growth rate, and then just click on generate the surface mesh. After this we need to describe geometry. Since my geometry contains both solid and fluid, I will choose the third option. Apart from that, I will keep other options as default. We don't need to change those default option for this case. So just click describe geometry. So we have two share topology methods here, and the one is joint intersect and the another one is interface connect method. So when we have overlapping surfaces of similar shape and size, we can use joint intersect method, and when we have already defined the interfaces, for example towards the fluid side and on the solid side, we can use interface connect method, and in that case we can specify both the interfaces which we want to connect. So for this case I will use joint intersect method, and for more information regarding this method I have given a link in the description of another source, and you can follow the link and can watch the video for further information. So I will apply share topology, and then I need to update boundaries, and I can check here the boundaries what I have already defined previously during the geometry stage, and the boundary type came correctly, so I don't need to modify them, and I can just click on update boundaries, and then it is asking the estimated number of fluid regions, and that is only the air region outside, so I will just click on create region, and then it is asking for regions whether it is fluid or solid. So I have two region, one is inner solid and outer airflow region, so ultimately two regions, and then I have to choose the boundary layers. So in this option I will change the default option to grow on solid fluid interface would be the better option, because that is where I want to capture the flow physics and as well as the heat transfer. And apart from that I will also change the total number of layers, so I will choose more number of layers since I want better heat transfer. So let's choose a little higher number, 10. Well it can depends on the problem you are solving, so I am choosing 10. And then after this stage, after adding boundary layer, you have to generate the volume mesh. So I will choose, or I can keep the default option, or you can also change. So for my case I will keep the default option and just click on generate volume mesh, and you can see a very beautiful mesh is created, especially near to the interface region where we have applied local sizing as well as we have specified the number of boundary layers. And let me check the total number of cells. This is more than how much, zero point 0.1 million or 1 lakhs. So overall that's all for meshing. Now we have to switch to solution, or you can close the tab here and can open from workbench also. I will just switch from here. You can also start setup from here, but Since I have directly switched from meshing tab, I don't need to follow that step, and I will choose the steady state, and I will choose energy equation. I will enable this option since I need to solve energy equation for conjugate heat transfer, and for simplicity I will keep laminar model for this case, and also I will choose default materials, which is air and aluminium, and also you can change if you want to choose another material, but for simplicity and timing I will keep the default fluid and solid. And then for cell zone condition, we have to choose fluid and solid options and define properly what kind of fluid is it. So this is air, so we are choosing air. And for heated cylinder, we are choosing the aluminium. So since we have not updated material, we are using the default material. And then I am also choosing the default operating condition, and one more condition in cell zone case I will define later. And this airflow and airflow shadow part is basically the interface, and this interior parts are two different zone, like airflow zone and heated cylinder, and inlet is basically the boundary which we need to define. So I will define it as velocity inlet, and I will give the velocity magnitude at the inlet boundary, and I will also keep the default temperature option here. And for outlet I will choose pressure outlet condition as the type of boundary, and for other conditions are default. And for wall I will take no slip boundary condition, which is the default condition. And for thermal condition I will also keep the zero flux for these walls. Well, you can change the option. And for cell zone condition, like I was talking about, for heated cylinder you need to define the energy generating source. So I will choose it as a source term. So I need to click on this tab and then go to source term, and now number of energy sources will be 1, and now I have to define the value here. So I will choose the constant volumetric heat generation, and now let me think about some reasonable value for this case. So yeah, I think 2 million maybe. Yeah, so let me choose this, that as the volumetric heat generation. So just click on OK, and now you have heat generating source inside. So that's very important boundary condition for conjugate heat transfer. And then I will keep most of the options as default, because the purpose of this tutorial is to talk about conjugate heat transfer. So I will off pseudo time step method, and then I will directly initialize using the hybrid initialization. And now I can also create the animation if I want to visualize the solution during the iterations. So that is very convenient, and that can be very useful sometimes, because we want to know how the solutions or how the heat transfer or other flow variables are going. But before that, let me define these parameters like number of iterations and reporting interval and profile update interval, and then I can define the solution animation. So just click on this tab, and I will define the contour which we are going to visualize after certain time steps during the calculation process. So go to contour, and I will create a new plane that will be YG plane as x equal to 0. So on this plane basically I would like to visualize the solution during the process. So that is plane 5, which is created now, and I want to visualize the temperature contour, and just click on save or display option. So since this is initial temperature, the solid cylinder is not visible now, but it will visible as the solution proceeds. So that's very convenient sometimes. And then I will go to run calculations, and since I have defined these parameters, and I will change slightly and just click on calculate. So yeah, your solution can take some time. So for the visualization or animation stage, as I was talking about, you can visualize after 10 iterations. So this is, well, that was the contours or contour which you can visualize during the simulation process. Now you can see how the temperature is varying basically. So yeah, so the next part of this tutorial maybe so if you have not subscribed to this channel till now, well, you can subscribe to my channel because it can take a lot of effort to produce this kind of technical video, and it involves a lot of stages, and your subscription, like or share gives us motivation to create more videos of this kind. So after this stage I will describe the CFD post stages, and we can visualize certain parameters there. And if you are a beginner, I recommend you to watch that part also and continue watching. And if you are already experienced user, well, you can skip the next part. So calculations are completed, and now you can also see the residual. Since this is not well converged, maybe we need to modify the meshing or certain other parameters, but that was not the target of this video or this tutorial. So let me close this part, and then we can start the CFD post processing and can visualize certain results along different planes or different surfaces. So let me click OK. So now we start CFD post. First we will refresh it, and then we can open or edit it. So I will tell you how to create planes, how to create contour, and more importantly how to visualize the temperature distribution. So first I will show you volume rendering also, but first I will create few locations to create contours. So I will go to location, insert plane, and I will give a particular name for the plane which I am going to create. Let's say symmetry 1, and let me create the plane on maybe xy and gx plane, y equal to 0, and I will also create one perpendicular plane. I will call it symmetry 2, and that will be similar, just I will change the method or plane, just hit apply. So these two planes are created. Now we can create the contours on this plane. So I will go to contour, and I will choose the location, and then I will choose the variable as temperature and local range. So basically this is the contour on a plane, and then I again duplicate it to create the contour on perpendicular plane. So now you just have to change location, and that's all. So this is the temperature distribution due to conjugate heat transfer. So you can visualize it beautifully. And the next part I will create the volume rendering. Basically you can see how the energy is transferring from fluid to solid. So just click on render, and then you have to choose the variable range, and this will be over all domains. So yeah, this is your volume rendering, basically how the energy is transferring from solid to fluid. You can actually visualize using this option. So I think that's all for this tutorial, and yeah, this tutorial has been very long, but I hope you learned something from it, and please subscribe to my channel, and you can like and share this video with your friends or colleagues. Thank you for watching.